All right, hello. Welcome to the second guest MFT talk of the day. I'm going to be talking about guest MFT for non-confidential VMs and protection against Spectre-style speculative execution attacks. So I'm from AWS. I work on Firecracker, which is the hypervisor powering AWS Lambda. And a bunch of this work is based on the work by Akali and Fuad that Akali was just talking about. So I'm not going to repeat the basic non-Coco support for guest MFT. Instead, I'm going to sort of jump straight into it. I'm going to give a quick recap of what exactly the Spectre vulnerability was, how those sort of Spectre attacks work, to set the scene for what exactly we're trying to mitigate against and what we're trying to implement into guest MFT. So specifically, how are we going to protect guest memory of KVM guests from Spectre attacks using direct map removal? And then at the very end, I will talk a little bit about some future work that a few of my colleagues at Amazon are working on, which is sort of a combination of how do we make things that work for today's traditional KVM guests work if the memory is backed with guest MFT, so post-copy migration, and KVM clock are the two things I specifically pointed out. And then specifically, what additional problems do we get trying to make that work with direct map removed guest memory? So for Spectre, how does this roughly work? It was this huge vulnerability. I think it was like around 2018 or something. I was still in uni when it happened, and one of my professors absolutely lost their mind and changed all of the class schedule. And then all of a sudden, we were talking about Spectre for a week. But the breakdown is essentially that CPUs do this thing called speculative or transient execution, where when they reach a branching instruction, they don't really wait for that to completely resolve. They sort of have a guess what could be the outcome of it, and then they happily execute along that guess. And sometimes they get it wrong. And sometimes it's even possible for someone to trick the CPU into specifically getting it wrong. And then at some point, the branching condition resolves, and the CPU figures out, oh, damn, shouldn't have done that. And it tries to roll everything back. But that also isn't really perfect. So for example, if there was a cache eviction, then we can't really roll that back all that well. And then an attacker can sort of look at like what sort of microarchitectural side effects were left over by such an imperfect rollback and sort of use that to infer data that the CPU loaded inside of this speculation window that actually really should have loaded because, for example, it speculated past some bounce check and accidentally loaded something from an arbitrary location, the direct map really shouldn't have. Usually there's like variants of this that come out all the time. And usually the approach to it is, well, we just like get a new mitigation and then you patch it, and then you either get like a new firmware version for your CPU, or you get like a new Linux patch of packages. So what we're instead going to be trying to do is we're going to see if we can find a more principled mitigation that just deals with this entire class of problems ahead of time, so that we have to worry a little bit less when there's like the next iteration, Spectre v5 or whatever we're at, eventually gets discovered. And the idea is essentially that we unmap all of the memory that we want to protect from all address spaces except the ones that actually own it. You can think of it as a sort of like reverse kernel page table isolation, where instead of unmapping the kernel pages from the user space page tables, do the opposite. We have some user space pages and we want to unmap them from the kernel. There's a Microsoft paper that calls this entire technique secret freedom. Amazon folks call it secret hiding. So that's all refers to the same thing. And the crux of it is essentially that if there is no page table to get to a specific physical page, then the MMU is going to say no during the speculation window, and if we never actually load any sort of data into any sort of caches or into any sort of microarchitectural whatever's in the first place, then there can't be any side effects. So that's the general idea of what we want to do. And so how do we apply this to KVM guest memory? Essentially, we unmap the guest memory from everything except from whatever owns it. In this case, it stays in the stage 2 EPT tables for the guest, because the guest needs to access its own memory, or in KVM, in guest memory terms, the guest even owns its own guest memory. And since we're doing non-confidential compute, it's also fine if the hypervisor keeps access to the guest memory, so it also stays in the VMM user space page tables. But everything else, we don't want it anymore. So we want to remove it from the kernel direct map, so that it's not possible to like take some sort of Spectre gadget that you might find somewhere in the kernel to leak the memory from another VM. And KVM specifically does retain access. That's the setup that Akali was mentioning earlier, where when you do this non-confidential setup in guest memfd, you give the KVM slot to guest memfd, but you also at the same time give it a VMA that is resulting from mmap of the guest memfd at the same offset at which you provide the guest memfd itself. And then KVM, for the most part, can continue accessing the guest memory via copy from user, copy to user, which works. If you just implement all of this, it works actually for quite a lot of KVM straight out of the box. There's two problems that you get. The first one is if you just use some existing direct map removed memory solution, you try to use it to back a guest. For example, you try to put a memory secret in there, then you will figure out, okay, guest page faults don't work because guest page faults by default they use get user pages, and guest user pages is not available for direct map removed folios. That mostly has to do less with get user pages needing direct map access because it doesn't, it just walks page tables, and more just that the caller of GAP has no way to promise GAP being like, look, I know this doesn't have direct map entry. I will also not try to use it because usually when you GAP a page, you will want to access it through direct map straight after. So GAP just rejects all of these folios. And that's exactly where guest memfd comes in, because guest memfd, Akali also mentioned it already, inside of KVM, it has a special fault handling where the page fault handler just directly consumes FD and offset. It never goes through any user space page tables. And so if we implement direct map removal into guest memfd, everything sort of just works straight off the box. There's one other asterisk with where does KVM itself try to ever access guest memfd direct map? It does KVM clock. I'll get to that a bit later, but for most very simple guests, if you disable KVM clock, that is actually all that's needed. And so, yeah, exactly as I was already saying, the setup would be the non-Coco setup that Akali described. All guest memory is shared in the Coco sense. The entire guest memory is shared, is mappable. It gets direct map removed. All guest page faults take the special guest memory default path so that we can do guest page faults in the first place. And the user space mapping of guest memory reflected back into the mem slot via user space address, so that copy from user, for example, if KVM needs to fetch an address to do MMO emulation x86, continues working. We have a patch series for it. I think it's V5 right now. I think after KVM forum, I'll post the next iteration. It's roughly 10 patches. Half of them are self tests. So really, there was not too much to do. The crux of it, we have a new address space flag, ASNO direct map, which unifies all of this gap handling for rejecting direct map from folios from gap with what memfd secret is already doing, so that we don't duplicate all of that. There's a new flag for guest memfd that just guest memfd no direct map, which causes guest memfd to remove folios from the direct map when they're allocated and reinsert them all back when they're freed. And this is supported when you need guest memfd, when you can manipulate the direct map at 4K granularity, which is not always a given, especially on ARM. And when guest memfd does not need to be accessed as part of fault handling, guest fault handling, which is also not always given, specifically on ARM, I found out. And so, yeah, it's actually x86 always works on ARM. You need this CPU feature, stage 2 FWB, and if the direct map is set up at 4K granularity at boot time. One caveat with our implementation, we don't do TLB flushes after we manipulate the direct map. And from a correctors point of view, this can't cause memory corruption or anything, because the mapping is not really invalidated. The mapping does not, the direct mapping doesn't really turn wrong. It's just that we prefer the host kernel to no longer use it. But if it sticks around in a TLB, then it's still the same memory behind the mapping, right? We do that mainly because TLB flushing is incredibly slow, especially on like these huge bare metal instance types that you have and like cloud providers, because you need to like send on like x86, you need to send an API to all CPUs and then wait for all of that to come back. And in our benchmarks, there was like up to 80% performance regression, which was not acceptable for Firecracker workloads. It should also be fine from the security point of view, because what would it mean to like try to exploit one of these TLB entries that stick around? You need to have the TLB entry before the direct map gets removed. So essentially, you need to already know that a page is going to, at some point in the future, contain something interesting before the guest even allocated that page. And then you need to keep the TLB entry alive until it becomes interesting, which sounds really tricky, given the finer TLB sizes and everything. And then on ARM, there is also some architectural considerations, which I'm not 100% sure on. So if anyone here has some insight on ARM break before make semantics, I would actually love to chat. In my mind, direct map removal and followed by direct map reinsertion at some point later in the future is like a really long break before make sequence. Like you break and then you wait a few hours and then you make. So I don't think I definitely don't think we would need to architecturally do a TLB flash on both operations. Maybe if we need to do one at some point, then we can maybe do it on reinsertion, and that's fine because that's not a hot path. But I also don't really think this can cause any TLB aborts on ARM because we're just restoring the same page table entry that was already there in the first place. So it's not like they can ever conflict, I think. I hope. Someone correct me if I'm wrong, please. But it works in our testing without the TLB flashes. And that's pretty much it for the basic support for this direct map removal in GuessMemFD. I'm now going to talk about some future work, which is mainly based on features Firecracker supports today for traditional VMs, which we'll also want to support for these direct map removed or secret-free VMs. And the first is a sort of post-copy migration, and the other is KVM clock, which Lambda needs for reasons. So post-copy migration, why do we need that in Firecracker? We don't do live update, we don't do live migration, but what we do is something called snapshotting, where essentially we have a VM that's running and we pause it, and then we dump all of the state, both the KVM state and the guest memory somewhere to disk, and then we kill the VMM, and then we wait some time. And then at some point we decide, okay, we want to continue using that VM, so we spawn a new VMM and we load in the KVM state, and then we load in the guest memory as well. And the guest memory as well, we load in lazily with on-demand paging. So whenever a guest tries to access a page, we sort of like fetch it from wherever it happens to be. So the setup is very, very similar to post-copy migration on this restoration path. And today, all of this, we do that via UFFD, because for normal VMs, you have the KVM page fault path for guests, and it goes through the VMA. And so if the page is not there, UFFD will get triggered. Obviously, for GuessMemFD, there is no VMA involved in the guest page fault path. So UFFD, at least for that, is already completely out of the question. And then the second question is then, okay, if our memory is direct map removed, how do we even populate it in the first place? So the first question about how to do post-copy migration for GuessMemFD is actually already answered by a patch series from Google, from James, which is called KVM user fault, which essentially you can specify a bitmap for each of your KVM mem slots, and one bit represents one GFN. And when the KVM gets a page fault for a GFN, which has this bit with its associated bit set to 1, then instead of just doing the normal page faulting routine, it just gives you a KVM exit, and then user space can deal with the page fault. So it's sort of like a KVM specific UFFD style notification mechanism. So that we can already do, we can use for the guest page faults. And then the only two questions remaining are, we receive this notification, how do we populate the memory? And then how do we deal with page faults that get triggered not through the guest page fault path, for example, because KVM does its MMO emulation and it does a copy from user. I mean, MMO emulation shouldn't cause a page fault, but you never know. Or if the VMM user space does some sort of page fault because of virtual device emulation, for example. And for the population, we first tried, okay, we have a VMA, so we could just mem copy into it, but that turns out to be really, really slow, because that then sets up a bunch of unnecessary page tables that actually no one ever needs, because KVM for its page faults never goes to those page tables. So the solution for that one of my colleagues, Nikita, came up with here is we can just implement the write system call for guest memfd. And as long as we only allow that system call to operate on unallocated ranges of the guest memfd, we can sort of first do the write into guest memfd before it gets direct map removed. And like this, we can populate our guest memfd. And this works. We have Nikita has a patch series for that as well. We have that on the latest slide. And for all other accesses, we are implementing UFFD for the guest memfd VMA, which is, I think at the moment we only support UFD minor mode, which is a bit, we're abusing it a little bit because normally the semantic for UFD minor mode is that you have a page that's already in the page cache, but only the page table is missing, and we're sort of, we expect the guest memfd page to be bolted in, and then after it, so we get a fresh page in the UFFD in guest memfd, and then after we trigger a minor fault, because it's really hard to do major faults, major fault handling for guest memfd. And then when we receive this minor notification, we populate the page VMM copy, and this is here is fine because, well, first of all, the user space page table entry we needed anyway because the origin of the fault was some sort of access through the user space page tables. And also, these are supposed to be a lot rarer than the guest triggered faults. So most of the faults are guest triggered, and most of the population we expect to happen through the write syscall. Especially when we like pre-populate, like for example, we get a page fault and then we populate the surrounding memory area as well. We do all of that, the write syscall. So these we shouldn't really be getting too much of that. There's some challenges related to that, which Nikita hopes to be talking about at LPC later because they're more MM related than KVM related. It's about KVM as a module, UFFD lives in core MM. It doesn't export any of the functions that you would really need to implement a UFFD for a file system defined in the module. And the MM folks also aren't really happy about exporting them. So there's some talks about how can we possibly allow this? Is the solution moving guest memfd into core MM after all? Can we provide some sort of op structure from UFFD that guest memfd can fill in at a sort of granularity that you don't need to export all of these MM functions? That is something that Nikita will be hopefully talking about at LPC in December. The other thing that we sort of need to get working is KVM clock. KVM clock is a bit special inside KVM because it actually accesses guest memory through the direct map. It's stored inside of something that's is called a GFN to PFN cache, where as soon as the guest sort of activates KVM clock through an MSR write, KVM resolves the physical address to a host physical address, and then caches this translation and listens to MMU and validation notifiers to figure out when it needs to recompute this. And obviously, if the guest memfd is direct map removed, then we can't access it through the direct map. And there is actually a mechanism inside of the caches that should account for this, where it tries to just memory map the page if it's not in the direct map. But because this is a page, these are pages that really should be in the direct map, memory map is going to be, well, this should be in the direct map, gives you the direct map address, and then it just doesn't work. So I talked to David about that a bit earlier, and it seems the solution here is not to go through just user space page tables, as I was writing here, but rather to teach these caches how to, or not the caches, but teach memory map to sort of figure out that even if it really should be in the direct map, you still get a new alias, a new virtual address alias for this page. So that's another thing that we haven't completely figured out yet that we need to continue working on. Sorry? Yes, there are more? Yeah, we haven't run into them yet. Do you know which ones they are roughly? Deal time doesn't use the cache yet. That's you sent the patch, so it hasn't been merged yet, so it's not yet a problem. Yeah, but there will probably be more such cases. Yeah, so if we just fix up the cache to work with guest memfd and to work with direct map remove guest memfd, that will also just work. hopefully. So yeah, that's something we'll be working on. And yeah, there's a few other things that I didn't talk about yet because they're also still in the quite early stages. We're interested in KVM prefold on ARM and specifically for guest memory. We're interested in the huge page of support for guest memory that Akali is working on. We've sent out a patch series for async page folds for guest memory and specifically async page fold with KVM user fold. But that's quite a few months old and lots of that has changed. So we're looking to send out a completely new version of that soon anyway. And yeah, if anyone wants to play around with it, we've got a Firecracker branch where we piled all of the patches onto some kernel. I forgot which one we're based on. I think still based on the V17 from Fuad from before it was merged. But we have all of the kernel patches, and we have a version of Firecracker that implements the new post-copy migration protocol for guest memory. It supports booting guests and doing I/O into diagrammatic remove guests. So that's available in our GitHub repository. And yeah, that's it. Thanks for listening. Yeah.
Do you have any idea on the performance impact of configure by user space address for the KVM internal accesses?
So we haven't really noticed anything in that regard, probably because there's not that many, especially because recently we moved from MMO transport for Virtuo to PCI transport for Virtuo, so now we do a lot less MMO anyway. But yeah, I think it's mostly, what does it? MMO emulation x86 fetches the instructions via copy from user. There's the page table walks that are involved in that fetch the instructions via copy from user. But KVM is doing that already anyway, right? So KVM is already doing the it via copy from user. So yeah, exactly. No. So is it actually completely unacceptable to sleep during the KVM clock update?
Give a better answer. Just don't expose any of them. Don't really any of them around there. It's awful. It will give you worse time. Just use the TSC. Turn it up. Make it up.
So the problem is, I tried that. At the beginning, I just disabled it, and then Lambda was like, oh, we need it, which I can talk to them about. Well, I agree, but that's an internal discussion to be having. But the bigger problem was that when I disabled KVM clock, then AMD guests wouldn't boot anymore because they can't learn about the TSC frequency in Firecracker anymore. Also, because on Intel you got the CPU ID leaf that tells it, oh, this is your clock frequencies. AMD doesn't have that, and well, that's also not merged. If it does get merged. Well, the thing is, even if we get it merged now, then we would need to update Lambda to use the guest but users here, which is going to be 6. Whatever. Yeah. Yeah. So that was fun. So for now, we do need KVM block, sadly. Yes. Well, guest memory is only a very small part of it, like a small part of a bigger story, because you still have all of the KVM register state that you would ideally also want to hide, and you still have whatever else is going on your host that you would also specifically want to hide. So just this is not enough to actually disable any mitigations. It might be a first step in that direction, but on its own, it's not enough. It's more so as a sort of defense in depth for when we have a new variant that doesn't have a mitigation yet, then we're at least protected via this. Yeah. Yeah, I haven't run into any of the others yet. I mean, okay, we don't do high. No, Firecracker doesn't support Windows, and Firecracker will not support Windows. No, we don't do Zendesk either. No. Yep. Sorry, what's that? Zone device mappings? I have. Oh. I have not looked into that yet, but that sounds. Oh, okay. I will definitely look into that. Thank you. And I guess do we have anyone from ARM here to answer my BBM questions? Okay, I will hunt down someone somewhere. Oh wait, yeah. So what's that? I didn't switch it. Yeah. So we don't pre-page tables because that's one of the things because ARM also doesn't allow like if you have the direct map set up at like using huge pages on ARM, then you can't do direct map removal in the first place because you can't break the direct map apart without doing exactly running into exactly your problem. So this only works if you did everything set up at 4-page granularity already in the first place, which thankfully it seems to usually be with default kernel configs. Well, there are no huge pages in the first place on ARM and for this direct map. On x86, we break them down when we encounter them. Yeah. Shit. Yeah. But I think if I remember correctly, for the huge pages, it does. If it breaks a huge page, then the direct map removal routine already unconditionally does the TLB flush. Because otherwise, I think MemTSQL also wouldn't work because that does flush TLB entries, but only for the 4K range. That was just direct map removed. So that the 1G flushing must happen in set memory invalid. That's a good point. I didn't think of that. All right. I think we're also almost at time. So thank you.